we came to four important conclusions based on the photoelectric emission experiment. Number one, the photocurrent started virtually the instant light was incident on the material. This meant that the actual emission process is virtually instantaneous. In reality, it takes place within 1 nanosecond or 1 billionth of a second. So, for all practical purposes, we can say that photoelectric emission is an instantaneous process with no time delay. Secondly, we understood that the amount of photocurrent detected for a particular frequency of light changed linearly with the intensity of the light. So, if you kept the color of the light constant and kept on increasing the intensity or brightness of the light, the photocurrent would increase accordingly. Third, the stopping potential, that is, the negative potential on the collector, which would completely stop the photocurrent, had no relationship with the brightness of the light but was completely dependent on the color of the light. Which means that once the photocurrent was stopped by enough negative stopping potential, no further increase in intensity would help you to start it back again. Lastly, we understood that for a given voltage and for a given material, there was a particular value of frequency which we call the threshold frequency, below which there would be no photocurrent emission no matter how bright the light we used. None of these findings were really meshing with the wave theory of light. As we said before, a wave is a continuous phenomenon, which implies that there must be some time delay between the incidence of light and the emission of a photoelectron, because it will take some amount of time for the electron to gain sufficient energy in order to release from the material. But we saw that this was not the case. Whether we were using low frequency or high frequency light, we saw that the photocurrent was essentially instantaneous. We also began to realize that the brightness of the light, which would depend on the amplitude of the light wave, was having no effect on the stopping potential. It was being controlled only by the frequency of the light wave. In order to reconcile these results with our understanding of light, Einstein came up with a new and novel way to look at the light phenomenon. He postulated that light was not really traveling as a wave through space. Instead, it was traveling like a cascade of individual particles, which he called quanta. Each quanta of light is containing a finite amount of energy which cannot be broken down further. He also postulated that the photoelectric emission was not a continuous process but a discrete process. What does that mean? Let's understand. In the earlier picture, we had a bunch of waves hitting the surface of the photoelectric material. Since the wave was transferring energy continuously, the electrons on the surface of the material would take a finite amount of time to capture enough energy from this incoming light in order to escape the material. Instead, Einstein proposed that rather than traveling as waves, they were traveling as particles, something like this. So, in this new picture, we had individual quanta of light traveling towards the material. And at any given time, an electron could either absorb or not absorb a single quantum of light. In other words, the photoelectric emission was no longer considered to be a continuous process. Each time an electron was capturing a single quantum of light or a single photon of light, and this was now considered to be a discrete process. In this particular picture, the energy of the photon would depend on the frequency of the light, and the intensity of the light would decide how many photons were hitting the surface. This new picture of light made more sense based on the experiments, because what we now understand was that the amount of electrons emitted by the surface depends on the amount of photons which are hitting the surface, because each electron requires an individual photon to be absorbed in order to get sufficient energy to leave the surface. This also explained the phenomenon of the threshold frequency, because if the photons had energy below a certain threshold, they simply would not be able to give electrons enough energy to leave the material no matter how many photons were hitting the surface. Because remember, at any given time, an electron could absorb only one photon. So this changed the way we look at the phenomenon of light and how it interacts with matter. Einstein showed us that we can calculate the energy of a photon based on this equation. K max is equal to h nu minus phi naught. So what does this equation mean? K max refers to the maximum kinetic energy of a photoelectron that has successfully escaped the surface of the metal. In order to escape the surface, it has to perform a given amount of work, and that is supplied by the photon that it has absorbed. This amount of work needed to escape the surface is known as the work function. If the photon had enough energy to overcome the work function requirement, it will escape the material with some spare energy, which will contribute to the kinetic energy of the escaping photon. The work function of the material depends on the properties of the material. For example, metals like potassium and sodium have very low work functions. They will exhibit the photoelectric effect even at visible light frequencies. On the other hand, there are other materials which have much higher work functions and will only show photoelectric emission for high frequency light like ultraviolet light. Secondly, we also see that the energy of the escaping photon has a linear relationship with the frequency. In other words, if we keep on increasing the frequency of the incident light, we are also increasing the kinetic energy of the electrons. This means that the voltage of the electrons depends not on the intensity of the light. We can rewrite this equation in terms of the voltage of the electron. As we know, voltage is joules per coulomb, that is energy per unit charge. So we can say that K max is equal to E multiplied by V naught, where V naught is the threshold voltage, and E V naught is equal to H nu minus phi naught, where phi naught is the work function of the material, nu is the frequency of the incident light, H is Planck's constant. So if we divide the entire equation by E, we get V naught is equal to H nu divided by E minus phi naught divided by E. So we have expressed the threshold voltage in terms of the work function of the material and the value of the incident frequency. You will note that there is no mention of light intensity or brightness anywhere in this equation, and that makes sense. The voltage or the kinetic energy of the photoelectron is completely independent of the intensity of the light. Remember, in this picture of light, the brightness of the light source tells us how many photons are hitting a particular surface. It does not tell us the energy of the individual photons, because that is determined by the frequency of the light, which is the term nu. Thus, using this now famous equation, Einstein was able to explain all the conclusions that we received from the previous experiments. And in this way, he conclusively showed that light behaves more as a particle and less as a wave.
Manorama Horizon. Learning made simple.